Hello, everyone. Good morning, good afternoon, good evening for you, wherever you join in today. So welcome you to the 6th Learning Lab session from Forecasting for Social Good. I am Harsha from Forecasting for Social Good. Today we have Dr. Nicola. She's a lecturer in Health Data Science at Lancaster Medical School. And she's an active contributor in the R community. And also she's the organizer for Our Ladies Lancaster chapter. So we would be really honored to have her as our instructor today because she's doing a lot of things in terms of R and sharing her knowledge throughout the community. Welcome you to the session today. Over to you, Dr. Nicola. Thank you.
Perfect. Thank you so much. I am just going to share my screen. Okay, hopefully that has worked and you can all see screen with some slides. Perfect. Okay, so a little bit of kind of an introduction to me and sort of what I do. So I'm a lecturer in health data science based in the Center for Health Informatics, Computing and Statistics. So my academic background is in statistics and forecasting and operational research. And then I worked in data science consultancy for a little while before I came back to academia. And as Harsha mentioned, I do sort of blog about R and data science as well. So in terms of what you can expect during the workshop, the session is going to run for 2 hours. There will be a combination of slides and sort of live coding examples, and some exercises for you to participate in as well. So it is, if you want to take part in the exercises, do make sure you sort of have R open in your laptop in whichever program you like to write R in, sort of RStudio or VS Code, whatever you like. And I would encourage you to ask questions in the chat throughout. I'll try and sort of check in every so often to answer those questions, and we'll sort of answer them at the end of the exercises as well. And I do hope that you sort of end this workshop with more questions than answers. So we are talking about generalized additive models, which is a huge, huge topic, and lots of things to kind of pick up and understand that we just can't cover in 2 hours. So I do hope that you have lots of questions by the end of the workshop. In terms of what I kind of expect from you during the workshop, I'm expecting that you're comfortable with simple operations in R, so that you can sort of load in data and do some simple calculations. I also assume that you're familiar with linear regression, you know what linear regression models are, how to interpret them, and how to fit them in R. In terms of workshop resources, the resources for the workshop are available on GitHub. So when I'm going through the sort of examples and stuff, if you want to code along with me, that's absolutely fine. If you also just want a copy of the code so that you can listen during the workshop, you can get a copy of the code on GitHub so that you do have it for yourself. So I will share that in the chat as well. Okay, so you can download a copy if you go to codes and click download zip. It will give you a zip file with all of the workshop materials that you need. There are also these slides, okay, and they are also publicly available as well. There's a link on the GitHub page. So if you want to look through the slides at a later point or follow along with them on your own laptop, you can do as well. So we are obviously doing a workshop about forecasting, and when we want to do forecasting, we do need some data. So the data that we are going to be working with today is modeling COVID data. So this is actually from the COVID-19 R package, which sort of collates data from countries all around the world. So for the workshop, we'll be looking at data for Great Britain and for France between sort of January 2021 and 2022. So what I'm going to do for the sort of examples is I'll demonstrate the R code on the sort of Great Britain data, and for the exercises you'll sort of do similar sort of things for the data from France. So for each day in the data set, we have data on sort of things like number of cases, tests, vaccines, deaths, and so on. And this is a really, really nice R package. I have pre-processed the data for this workshop a little bit, but you can have a look at that package and at that resource because it is very, very good. So you can download the data that we'll be using for the workshop from GitHub. I will copy and paste that into the chat as well so that you don't have to try and read that off the screen. And I'll share that again. It's in the workshop resources on GitHub as well. And the data folder on GitHub shows you the pre-processing that I've done. So it's just sort of filtering out to different dates and different countries and things. Okay, so let's actually sort of get started with content now that we've got the sort of housekeeping and details out of the way. So for the first part of the workshop, what we're going to look at is essentially what are generalized additive models and sort of why do we need them. So thinking about why do you need another type of model? So sometimes when you have data, not just time series data for forecasting, but any type of data, sometimes it's quite easy to see what model might be appropriate. You can look at the data and say, okay, that looks sort of like a straight line, or maybe that looks like some sort of curve or quadratic. And if you're looking at time series data, sometimes you get nice data where you can see these seasonal patterns really clearly, or you see something sort of very spiky and you start thinking about maybe ARIMA models or some sort of smoothing. And you can kind of get an idea of what sort of relationship might be in that data and what might you want to model. But other times you get data. So for example, like the COVID data we're going to be looking at, where it doesn't really look very clear. You can't look at that and guess, how does that change over time? What equation do I fit to that line? So that's why we look at things like generalized additive models, okay? So if we start with a really simple case of just linear models, okay? So you're modeling some variable y, some outcome, and it's some linear combination of an intercept value and some with coefficients of your explanatory variables, so different factors that might be impacting your outcome. And then you have your generalized linear models, okay, where you're modeling some function of the outcome. Okay, so it's quite common if you're looking at binary data or you're modeling probabilities, you want to make sure that the thing you model is between 0 and 1 because probabilities are between 0 and 1. Or you might want to, if you're looking at count data, look at modeling the sort of log of the outcome sort of on a log scale to make sure that it's always positive. And essentially generalized additive models are another extension of this. So they're essentially a sum of smooth functions of the explanatory variables. Okay, so we can still model some function of y, and that is equal to your intercept plus some smooth function of one explanatory variable plus smooth function of something else, and so on. And these smooth functions, it can essentially be any function. They might be something really simple. They might actually just be a straight line. Okay, it's perfectly fine to go for the simplest case and fit a perfectly smooth straight line, but you might have quadratics or you might have some more complex functions. So in terms of generalized additive models, when you're thinking about modeling those complex relationships, like you saw in that example with the COVID data, there's a range of things you could do outside of sort of generalized additive models. You could do something really complicated. You could have some sort of black box machine learning model that tells you, reasonably well, what is your prediction for a particular value, what is your forecast. But the nice thing about GAMs, generalized additive models, is that they sit sort of somewhere in the middle between linear models, which are not very flexible. They're quite hard to fit complex relationships, but they're very easy to interpret. Okay, with a linear model, you can say if I have a unit increase in this variable, then I expect that the outcome will change by this much. If you have sort of black box machine learning models, they're very flexible. They can do lots of different things. They can model complex relationships, but they're quite hard to interpret and they're quite hard to understand what is it that's affecting your forecast. So the nice thing about GAMs is that they're in between. They're not quite as easy to interpret as linear models, but they're a bit more flexible. So it gives you that sort of nice middle ground. So we're thinking about GAMs in practice and thinking about generalized additive models in R, there are quite a few packages for fitting GAMs in R. The two sort of main packages are the GAM package and the MGCV package. For this workshop, we'll be using the MGCV package. It is what I tend to use on a daily basis for this. Mainly because it's a little bit more flexible than the GAM package. It has some nice features. One thing I would recommend is that you don't load both packages at the same time. Okay, so you might have both GAM and MGCV installed, but I wouldn't load them into R at the same time because, as you might expect, there's quite a few similar functions between them. So if you do load both at the same time, restart your R session before you load MGCV. So let's actually have a look at fitting a GAM in R. Okay, so I am going to use Posit Cloud today just because then I can be sure that I've loaded all the packages that you actually need and I don't have anything hidden lying around in the background. So we're going to start off by loading the packages we need. So I am going to load the tidyverse. That is technically optional. Oh, this hasn't installed. What I'm going to do instead is load dplyr because I think that's the only one I actually need for the first part of the workshop. And we're going to load the MGCV package as well. Do let me know if the text on screen is a little bit small. If you need me to make the text bigger, I can do. Okay. And then we're going to load the data in from GitHub. Okay. And what we can do, first of all, is have a little look at this data. Okay, so we can use the view function in R to inspect our data. Okay, so you have this sort of country code, the date, the number of deaths confirmed, tests vaccinated, people vaccinated, etc. And at the end, I've added some additional columns. So I have this column date obs. Okay, so this is the sort of number of the observation in terms of date. And we have the day column, which is the day of the week. And I can see people want a little bit bigger text, so I will do that now. Is that all right? Okay, hopefully that's okay. Do just message again if you want the text a little bit bigger again. Okay, so we have our data here. So the reason that I'm sort of made this date obs column is because the GAM function in R is not sort of set up to work with date objects. Okay, so this is a sort of actual date class in R. It doesn't like sort of using them as explanatory variables. So you've got a couple of different options for how you deal with this. You can do as numeric on dates, or I've just sort of essentially looked at row numbers. Now, if you are very closely looking at the data, you will notice that there are some rows missing. So if you look at the date obs, you'll notice if you go down far enough, there are sort of jumps between observations. And so the reason for that is because when you load in the data and you look at the counts, some of the counts are negative. Okay, and obviously we can't have a negative number of cases of COVID. So we have some missing data. And you'll see that that's one of the things that the generalized additive models deal really well with. There are some forecasting approaches that you have to have equally spaced data in order to be able to fit them. And they don't deal well with sort of missing data, and you have to think about imputing values. But with GAMs, we don't actually have to worry about that. It doesn't matter if our data is equally spaced, if they're collected at completely irregular intervals, or if you have missing values, which is one of the reasons they are quite nice for working with data, because quite often, even if you do have regularly collected data, you will have some that just are missing or sort of corrupted values like we have in this case. So what I'm going to do first of all is I'm going to subset the data to look just at Great Britain data to start with. Okay, so we'll just look at modeling one country at a time. Okay, so we can filter based on the country code is sort of Great Britain. Okay. And then what we're going to do is split our data into training and testing sets. Okay, so we want to fit some different models to our training data and pick whichever model we think is best, and then try to predict the values in our test set and evaluate them against that to see how good our forecasts are going to be. Okay, so you can choose what proportion of your data is training and what proportion is testing. I'm going to use 80%, so fairly standard. Some people go for 75. If you're following along or when you're doing the exercises, do feel free to pick whatever you prefer. Okay, so let's see how many rows of our data we're going to put into the training set. Okay, so take that training proportion and multiply by the number of rows in the data. Okay, and I'm using the ceiling function just to round up because we want a whole number of, that's bracket in the wrong place. Okay, so I'm going to have 291 values in my training data. Okay, so I can subset that using square brackets. Okay, and I'm going to save that as GBR train. And then I want to do something similar for the test data and get essentially the rest of it. Okay, so let's do, so start one row higher up than our training data and go up to the total number of rows in our data. Okay, so hopefully this works. Okay, and you can view the data again just to make sure that it's actually worked, or look at the number of rows. Okay, and you can see that this looks roughly as we would expect. I can see there is a question in the chat, which is a very good question. Shouldn't we do some sort of random split of the data? Okay, so rather than taking the first 80% as the training data, shouldn't we take some sort of random selection of the 80%? And if you are working with data in general, yes, you absolutely should. But we are specifically looking at time series data. So we're looking at data over time. So we want to be forecasting into the future. So we always have to take blocks. Okay. There are sort of different approaches to how you can do that, but the easiest way is to just look at the first 80% and then forecast forward for that remaining 20% of the data. And naturally, the first thing we want to be looking at when we have data is thinking about what does it look like? Okay, so this is our sort of question of what types of models might be appropriate. Okay, so we have, let's look at date on the x-axis. Okay, put time along the x-axis, and what we're going to be modeling today is the number of confirmed cases. Okay, so dataset $ confirmed cases. Okay, and you can see that that's our sort of same plot that you saw in the slides earlier on. Make it a line plot, it's a little bit easier. Okay, you have sort of high initially, then this big drop, then a sort of spike, and then some sort of ups and downs again. Also, from first glance, it looks like there might be something sort of seasonal going on. Okay, we have these sort of peaks and troughs going up and down as well. And what you can do is you can also look at some other variables in the data set and start to think, okay, is the number of confirmed cases is probably not just dependent on time. There's probably some other variables that might help to explain it. So for example, you might want to look at things like the number of tests, okay? So you can do some scatter plots to look at whether there might be some sort of relationship between other columns in the data set and the one that you're actually interested in. Right. So you can make some scatter plots and look at some relationships. Now, to just sort of get you started with using the GAM function in R, what you can actually do is just fit a linear model to see. We know that it's not going to be a good fit, but to sort of get you started with how does this GAM function work. Okay, so from the MGCV package, you have the GAM function, and it's very similar to the LM function in R and to the GLM function. So if you've used either of those before, this should look quite familiar. Okay, so you're putting your sort of outcome, your variable of interest, on the left-hand side of the formula. So you have confirmed and then a tilde, and then in this case, you can look at date underscore obs. Okay, so putting that number of date observation essentially in here. And then using the data argument to say that our data comes from the training data set here. And what you can do is you can save that as an object. Okay, so let's just call it LM GAM. And because I haven't specified any sort of particular type of smooth function or any particular type of distribution, it just defaults to assuming it's a normal distribution and fitting that straight line. And you can see a lot of the, as we go through it, you'll see that a lot of the functions in R that are designed to work with the LM function or the GLM function also have versions for GAM that do the same thing. Okay, so if you want to pull out what are the coefficients from the model the GAM model you've just fitted, you can use the coef function, okay, and do LM underscore GAM, and this tells you, okay, here's the intercept value, and here's the slope coefficient. Okay, and if you want to see what that looks like, you can, of course, take your plot and add a line to it. So you can use the lines function in R. So we have our date obs. Okay, and I'm going to change that one as well. Okay, and then if you want to get the fitted values, you can do sort of your model object $, and you get the fitted values. Okay, if you want to make that a red line, so it's a little bit easier to see, you can add that. Okay, so you can see that if you use a GAM function and you don't add any additional information than you would if you use the LM function, you essentially get the same output as you would with the LM function. Okay. So, yeah, the example code is on GitHub. So I can see that that has answered the next question. Yeah, I'll post the link to GitHub as well, again in the chat in case you missed it earlier on. So the example that I'm going through are on GitHub as well in the examples folder. They might not be identical to what I type because I'm kind of working through it live as we go, but it is roughly the same there if you do just want to concentrate. But it is now your turn to actually write some code as well. Okay, so if you're looking at GitHub, you can go into the exercises folder. If not, the instructions, I'll leave them on screen. So if you go ahead and open up R and load the packages required for the workshop, mainly the MGCV package, load in the data for the exercises and subset it to look just at France. Okay, so it's the same data I'm working with, but if you look at France rather than Great Britain, go ahead and split the data into some training and testing sets. Make some plots, so have a look at confirmed cases over time, see if it looks similar to the UK or whether it looks different, and then go ahead and fit just a linear model using the GAM function from MGCV. Okay? I'll give you some time to work through that. If you need more time or you need less time, that's absolutely fine. If a couple of you start sort of messaging that you're done with the exercises in the chat, that would be great, and then I can check in on time. And if you do have any questions, I will try and work through them. I noticed that Martine has definitely pointed out a helpful thing that when you're we looked at splitting into training and testing data, taking the first 80% worked really well, assuming that your data is in incorrect time order. So thank you for pointing that out. That is absolutely correct, and I know that my data is in time order in this case. All right. So have a go at the exercises, and if you do get stuck, feel free to just ask for help. Okay. Okay, I can see that a couple of you have started sort of working through this, and that you're starting to find that the linear models are probably not a great fit as we would expect, and that it's quite spiky, and there's probably some seasonality in there as well. Yeah. Do you all just sort of let me know when you are ready to move on to the next section as well? Okay. Yes. Okay, I think quite a few of you are done and ready to move on. And as Adrian has pointed out, if you do a linear model with sort of no accounting for the fact that it's count data, you will end up with negative COVID cases after a long enough time of fitting your model, which is obviously not what we want. So let's move on to thinking about, well, how do we fit something that's much better than that? And just a note again that the solutions for the exercises are also on GitHub. So those are in the exercise solutions folder. So if you download that, or you can view them online, so that if you don't manage to finish an exercise in the time, you do still have a sort of version there ready for the second exercise that you'll need the data and the data split for. Okay, so let's think about this sort of GAM function and the MGCV package, and think a little bit more about how do we actually fit proper generalized additive models in R rather than just linear models. So we want to fit some sort of smooth function to each predictor. Okay, so if you remember when we go back, I think my screen's frozen, which is not great. It's unfrozen on exactly the right slide. So our generalized additive models are essentially just a sum of smooth functions of our explanatory variables. So what we need to do is we need to figure out what is this smooth function of each predictor. So what we're going to do is add together a bunch of other functions. So each smooth function is going to be some sum of other smooth functions. Okay, so we might have all these different sort of basis functions here. You might have some sort of cubic polynomial. Okay, so you can see each line here, you have some straight lines, but you also have different types of polynomial. And if you add them all together, you get the black line. Okay, so you get something that's a smooth but very flexible fit. And you can kind of start to imagine how flexible this modeling framework can be. Okay, you can add together essentially as many different basis functions as you like, and these basis functions can themselves be quite flexible and take different shapes. So you can sort of add together lots of functions to get almost any sort of complex smooth function here. So the way we do that in R with the GAM function is, instead of just putting in the predictor on the right hand side of the data of the formula, sorry, you wrap it inside some smooth class. Okay, so it's most of the time it's this S function. Okay, so that is a lowercase s, and you put your variable inside that. There are technically some different versions of these smooth classes. Okay, so as well as S, you have sort of TE, TI, and T2. S is probably the most common, but you can use these other classes to sort of as building blocks for doing something called tensor product smoothing. But during the workshop, we'll be using the sort of S class of smoothing, looking at splines. Okay, so there are different types of splines of these different types of basis functions. Okay, so which functions on the left-hand side, which ones are you going to use? What types of functions might those be? There's different types. And inside the GAM function, the BS for basis argument lets you decide which type you want to use. And we'll look at the sort of help files for smooth.terms to give you the details, so you can see all the different types that are available. You can also include multiple predictors inside the GAM function in exactly the same way that you can include multiple predictors inside the LM or GLM function, is that you just add them together on the right-hand side of the function. You can use both different types of smoothing for each one, because you can imagine if you have different predictors on the right-hand side, some of them will have different sort of types of smooth relationships. So you want that flexibility, but you can also include non-smooth terms on the right-hand side. So you can have some combination of smoothed variables and sort of non-smooth variables. It's reasonably common for things like categorical variables to be included on the right-hand side as well. And of course, we also have the sort of classic question when it comes to any sort of smoothing is how smooth is smooth enough? Okay, so you might have a sort of, in this example, some very smooth function, okay, or you could have something that's quite wiggly. And this is a hard balance, and there's no perfect answer to this problem. So if you're thinking about forecasting in particular, you want to make sure you're not overfitting. Okay, so if we pick a function that's a little bit too wiggly and fits too closely to our training data, when it comes to forecasting into the future, it's probably overfitted on the training data and it's going to be hard to predict. Okay. But equally, on the other side, if we pick something that's too smooth, we might sort of lose an important part of the relationship or particular trend that we don't pick up. So it's going to be a balance between the two. And in R, you can change the level of smoothing with the SP argument. And you can control that either in the GAM function as a whole for sort of all terms in the model, or you can change it within each S function. So for each explanatory variable individually, you can have different levels of smoothing for each one. The other argument that's quite commonly used to change how wiggly or how smooth the fit is thinking about the number of basis functions that you have. Okay, so again, if we jump back here, okay, so I think in this example, if I remember correctly, there's something like 10 different basis functions here, and you're adding them together. If I only added 2 of them together, I would most likely get a less wiggly function. It would be a much smoother fit. Okay, so let's look at some sort of practical examples of this. Okay, so go for example 2 if you are following along or want the code at the end. It'll be in the example 2 file. So let's actually fit a GAM using the GAM function with the S smoothing. Okay, so it's going to look very similar to the model that we had in the previous example. Okay, so it's going to be GAM function bracket confirmed tilde, and then here we have S, so a lowercase s, and then date obs, and specify that our data is coming from that training data. Okay. And you'll see this time when you run coef of GAM1, okay, so to get the coefficients out from that fitted model, okay, you get a lot more than just your intercept and your slope. Okay, so here we're fitting a model with sort of different basis functions, and these are essentially the coefficients for each of those basis functions that you're adding together. And if the other sort of functions that you typically use with GLM will also work here. Okay, so if you want to get a summary of the model, you can use the summary function. So you can do summary of GAM1. Okay, and you can see that it gives you reasonably similar outputs to the GLM or to the LM functions. Okay, so it gives you a sort of summary of what model you actually fitted, what is the intercept for the model, and it also gives you the sort of significance of the smooth terms. And I want to kind of really highlight here that these are approximate significance. Okay, so don't sort of look at p-values and look at them as some sort of hard line of exact and assume that they're exact values and use this to think about whether something's truly significant or not. Use it more as a sort of loose indicator of what might be important in your model. And you also get some other summaries, so you get things like your adjusted R-squared and the amount of explained deviance in the model as well. Now, quite often, well, at least personally, I find it very hard to tell whether a model's any good from this type of output. What I want to do is I want to plot it. Okay, so I want to see, does the fit of the model look anything like the data that's underlying it? So what you can actually do, first of all, is look at a plot of the model object. Okay, so you can do plot of GAM1. What this plot is, it plots the smooth line for each linear predictor. Okay, so here we only have one predictor on the right-hand side, so it just shows you what is the smooth line of that date obs over time. If we want to actually plot the fitted values, we can do the same thing as we sort of did for the linear model. So I am just going to copy and paste this code to save me writing it twice. But here, instead of plotting the fitted values from the LM one we did, we'll plot from GAM1. Okay, so here's a plot of our data, and this is a plot of our sort of fitted line from the generalized additive model. Okay, and you can see that first of all, it's a lot better than the linear model, and it's captured quite a lot of the structure of the sort of general trend. Okay, especially in the first half, it's doing reasonably well. In the second half, it's not doing too great. It's kind of missing the fact that there's three kind of spikes here. It's sort of only picking up two of them. So let's think about how can we fix that? What else might be going on? So there's sort of two things we can think about. So one of them might be the same thing you think about with many models is there something I'm missing? Okay, is there some other additional terms that might tell you something else about the data? Okay. So if we think about our data set, what else is in there? Okay, so we also, if we're modeling confirmed cases, maybe that also depends on the number of tests, might be related to the number of vaccines given or number of people vaccinated, for example. It might also depend on the day of the week. Okay, so if you're looking at the plot of the data initially, it does look sort of seasonal. Okay, there are these sort of ups and downs even within the trend. So we might want to think about how do we model the day of the week. So we'll start by thinking about, first of all, adding an additional term for tests. Okay, so let's create a second model, okay, using the GAM function again. Okay, so it's going to be confirmed till the smoothed date object, so over time, plus some sort of smooth function of the number of tests. So it's up to you, and you need to think about it a little bit, is does it make sense to include a smooth term for the number of tests? Does it improve your model? Okay, and again, specifying data is equal to our training data, and we can look at the summary of that model instead. Okay, and you can see here, okay, it's explained a little bit more deviance than the previous model, both p-values look highly significant. Again, obviously taking that with a pinch of salt, but let's look at the fit of that model. Okay, so how well does this model fit compared to the previous one? So what I'm going to do is I'm going to print it in blue. Okay, now that doesn't actually look particularly helpful. Okay, the overall trend is pretty much exactly the same. Okay, that blue line is sort of following the same line as the red one. It's just a lot spikier. Okay, and that's because the number of tests is changing over time, and it's probably changing from day to day quite a bit. So we're getting this sort of weird spiky behavior that isn't really helping. So let's think about the other approach of, well, adding in that seasonal component, okay, adding in something that captures the day of the week. So again, there's so many different options for how you could do this. You could do this almost include it as a categorical variable, okay? So almost thinking about having a different smooth line for each day of the week, potentially as time goes on. So modeling almost like a smooth trend over weeks that varies by day. The other option is that we include a smooth term for the day. Okay, so we treat it as a continuous variable and say that it's some smooth function, that the number of cases is changing in some smooth way over the course of a week. So let's have a look at how well that approach works. Okay, so if we do confirmed, again, date obs plus a smooth function over day, we'll do data is equal to our training data again, okay? And what you notice is that you get a nice error message, okay? So what this error message is basically saying is this term has fewer unique covariates than the maximum degrees of freedom. And this is a little bit, it feels like a little bit of a cryptic error message. What that's basically saying is that the number of unique values in the day column, okay, so obviously there's seven days of the week, that the number of unique values in that column is less than the number of basis functions that you're trying to use. Okay, so if you're trying to fit 10 basis functions to only 7 data points, that doesn't quite make sense. Okay. And it is worth noting that the default number of basis functions in S when you're fitting GAMs is 10. Okay, so you can look at the help files. Okay, so if you do a question mark and an S, okay, so S is the dimension of the basis is K. And if you look at the sort of choose K documentation, you'll see that it comes out as 10. Right? So we can say that the maximum size of the basis is 7. Okay, for 7 days of the week. You can choose less than 7 if you want to, and you might be able to. We'll kind of look a little bit later on in the next section about how do you choose the value of K and how do you choose the value smoothing. Okay. So we want to look at a summary of this model. Okay, so if we do a summary of GAM3, okay, you get the sort of output looking at the general trend over the observed day, as well as the day of the week. And if you want to plot that as well, okay, we can plot this, okay? And again, you're still getting that same trend, okay? That hasn't changed. The trend here is defined by the date obs, but you're starting to pick up some of that seasonal component. So you can see that the spikes in the sort of seasonal bits are matching up with the spikes in based on this day of the week. Okay, so I can see there's a couple of questions in the chat. We'll cover some of these in the next section. I'll pick up the first question around is k equals 7 in reference? It's just in reference to the smoothness of day. Okay, so you can see here this sort of k equals 7 is wrapped inside the s function. So it is applying only to day here. Okay, and I'll come back to the other questions about sort of model comparison and thinking about AIC values in a little while. Okay, so I'm not ignoring your questions. I can see them, but I will answer them in a second. So we've seen this fitted values, so maybe we still have a bit of work to do with the trends, but overall the seasonal component is there. So we also want to think about how do we control how smooth the fit is, as well as thinking about how many basis functions, thinking about the level of smoothing. And we can do that with the SP argument inside that S function. So let's fit another model. So we can do gam confirmed tilde S of date ops and data is equal to GBR train. Now here, obviously, we've seen that including day is useful. I'm not gonna include it in this version just because it's going to make it a little bit easier to see the effect of smoothing if I only have one thing to think about smoothing. Okay, so this is what our default level of smoothing looks like. So we can change that with the SP argument. Again, this is inside the S function here. So if I had multiple terms, I would apply this level of smoothing only to date ops. Okay, so if I do something like 0.8, okay, you can see I get an even smoother curve. Okay, so you can go back and forward. This is the default value. If you choose a value that's higher, it's smoother. So a bigger value here is much smoother. Okay, so if I go for something smaller, okay, I get something a bit wigglier. Okay, so it is controlling the amount of smoothness based on this value. So big values are smoother curves. Now, the question in the chat, which is what's the default value? Well, the default value is that the GAM function tries to work out what's the best value. Okay, so you might have a particular reason why you want something to be smoother than the GAM function is choosing, and you might want to manually change it with SP, but quite a lot of the time you want to try to figure out what is the best value. And the GAM function does that automatically. So it doesn't come up with, it doesn't always fit it with an SP value of 0.3 or anything like that. It's thinking about what's the best value for this one. And there's different methods for choosing what's the best value. Okay, so if you look at the help files for GAM, okay, and you scroll down to methods, okay, you'll see the different methods that you can use to estimate that smoothing parameter. Okay. What I typically do is use REML, okay, as it's not the default. The default is a sort of cross-validation method, but I typically use something based on maximum likelihood. So you're looking at REML instead. Okay, so what you can do is instead of specifying SP here, you can say method equals REML. Okay, and I'm going to add that day smoothing back in as well. Okay, so this will be sort of model number 5. Okay, and that will plot it automatically. In this case, the default method of choosing the smoothing parameter, it gives you pretty much the same thing regardless of which method you use, just based on the sort of size of data and things we're looking at in this example. It's not too different. So far, we've kind of looked at how do you plot things in base R, and how do you plot things using the sort of plot objects within the GAM function. I want to very briefly mention another package, which is specifically designed for plotting GAMs. Okay, so what you can do is use the draw package on a GAM object. Okay, and this creates basically ggplot versions of the smooth function for each explanatory variable for the smooth functions. So you can see, okay, here's how the smooth function looks when we're looking at date obs, and this is what the smooth function looks like for day. Okay, so you can see that there's sort of a bit of a lag in potentially when cases are confirmed. Okay, so you can think a little bit about interpretation here. Okay, so you might be thinking, okay, maybe more people go out and socialize on the weekend, and then it takes a few days for symptoms to appear, and then a few days for sort of tests to actually be confirmed, and that's why you might get spikes in cases on particular days of the week. Okay, so it's thinking about, you can interpret the smooth functions for each of your explanatory variables as well. Okay, so if we hop back to the slides, I think it is your turn to have a go at doing some more exercises. So if you're looking on GitHub, you can see these prompts, the instructions on screen. So what I'd like you to do is fit a generalized additive model to the COVID cases, confirmed cases in France, using the GAM function with the sort of S for spline smoothing. Try adding in a different additional term. So have a look at the data and see what might improve the fit. Think about varying that smoothing parameter. Does choosing a value yourself change the fit of the model? And then plot the smooth functions for the predictors and the outcome to see how well your model fits. Okay, so again, I'll give you some time to work on that, and if you just pop a message in the chat again to say that you're ready to move on, and I will have a look at the questions that have just come in and answer them after you've had a go at exercises. Okay, I can see that some of you are starting to finish exercise 2. If the rest of you do, just sort of let me know when you are ready to move on to the third section. Oh, perfect. Lots of people. Excellent. Okay. So just as a reminder that the exercise solutions for exercise 2 are also on GitHub in the exercise solutions folder. Okay, so let's think about making predictions with uh, generalized additive models. And I'm hoping that this section will answer some of the questions that are in the chat. So when we're thinking about models, after you've fitted your generalized additive model, there's probably a bunch of questions in your mind. Is it a reasonable model? Okay, are the variables that you've included the right variables? Is having a smooth relationship for those variables the right thing? If you fitted multiple models that, as in we've done here, which one is best? Is the model you fitted better than other models that you could have fitted? How well does it actually fit to the data? What are the forecasted values? Okay, so if you're looking at forecasting in time series, you're thinking about what are the forecasted values. You might, if you're not in a time series context, you might be thinking about what are the predicted values for some other potential predictions you want to make. And you also probably want to think about how do you interpret the model. Okay, so it's one of the things that once you've picked a model and you've made some forecasts, you really want to be thinking about, well, what is it that's contributing to that forecast? So we're going to look at each of these different things. So if we go into example 3, what we're going to start with is thinking about model comparison and thinking about how do you choose different models. Okay. And the good thing here is that most of the approaches that you use for generalized linear models also work here. So things like looking at the AIC values and comparing them. Okay, so if we look at for example, the second model we fitted, okay, so the simple model with just the obs in it, and compare that to the last model we fitted, so say GAM number 5, I think, you can see that including the additional term for day of the week, the smooth term for day of the week, reduces the AIC. So it is a slightly better model, even though it's increasing the complexity of the model with having another smooth function and another 6 or so parameters in the model. And when you're thinking about, well, how do you decide, should I include day or should I include tests or anything else? You can think about things like AIC, particularly if what you care about is sort of how well it fits. You can, I think there was a question in the chat earlier thinking about, can you, if the p-values are only approximate, how can you tell whether the new term that you've added into a model is significant or not? So I would typically look at things like AICs, think about, does it actually improve the fit of the model? When you're thinking about p-values, doing things like sort of stepwise adding in variables at a time it's not always a great approach for variable selection. You can end up sort of going down a rabbit hole depending on what decisions were made early on. So I would say sort of use them more as a rough guide. If you get that the p-value when you look at the summary is very, very small, you can be reasonably sure that it's a significant term. But we'll see again in the next section some of the problems that you might have with including different variables. And when we're thinking about, is our model any good? And particularly when you are thinking about, is this the right level of smoothing for this variable? Is this sort of the right variable to include? there is actually a nice function called .check in the MGCV package that will run some sort of basic model diagnostics for you. Okay, so if we run gam.check on our last model, you can see you get a combination of some printed diagnostics as well as some plots. Okay, so there's quite a lot of information here. So one of the things that's quite interesting is looking at the basis dimension. Okay, and it does some tests to check, is the number of basis functions that you have, is it too low? Okay, and this is essentially what these p-values are looking at. Now, obviously for day, there's kind of a limit to what we can do because we only have 7 unique data points. But you can see for date obs, this p-value is sort of very, very significant. And what that's suggesting is that if that p-value is very low, then it sort of indicates that the number of basis functions is a little bit too low. Okay, and remembering that the default that you put in is k equals 10. So you can look instead at changing the value of the basis size, essentially. Okay, so that's sort of what this model check here is suggesting, is that for date obs, we don't have enough basis functions. So if we look at changing that, okay, so we do confirmed S for smooth function, date obs, and let's try k equals 20. Okay, so double the size of the basis functions. I don't want to put test in, I want to put day, and k equals 7. Okay. And again, put our data in and method to choose the smoothing parameter. Okay. So we can again look at the summary of this model. Okay, so you can see that the both are coming up as very low p-values. So even though it's an approximate significance, because they are both very, very small, you can be fairly sure that they are both significant terms here. Part of the problem with thinking about significance of functions is that, you know, the significance of a particular variable might be changing. Okay. So you can rerun your gam.check function to see if that has improved things. Okay. So you can see that here, a couple of interesting things have happened. Okay. So even though we changed only the size of the basis for date obs, the p-values for both date and day are changing here. Okay, so if we increase the basis size for date obs, we can capture a little bit more of the wiggliness of the function. So maybe we don't need day to be as wiggly as well. Okay. You can see that this is still sort of very significant, so maybe we do need to make it even more, even sort of larger basis. What I'm going to suggest is that we actually plot the output and look at it before we go ahead and just keep adding basis functions to each one. So I am going to copy and paste the code from the previous example. Okay, so we can look at gam number 6. Okay, so here is our original data, and you know what's gone wrong here. This is interesting. Yes, you're absolutely right. When I fitted the GAM, I fitted it to the whole data set exactly. Thank you. Okay, so this is one of the downsides of autocomplete is that in our studio it sometimes picks the wrong one. Okay, so here's our data and here's our fitted values. Okay, so you can see that this does capture those spikes towards the end a lot better. Okay, so I think when we looked at the sort of default with k equals 10, it was only really picking up two sort of spikes here, but we are now picking up all three. And obviously, if you keep increasing k, you're going to get something, that fits even closer. But when it comes to thinking about forecasting, getting as close as possible to the fitted data isn't always what you want. Okay, and this is a case where we're looking at COVID data, so it is very much real data with unexpected spikes that if you're thinking about forecasting trends, you need to think about whether you really want to fit very closely to essentially outliers and spikes as well, which is what will happen if you choose a very large value of k. So we can also think about predicting and getting fitted values. Okay, so you've already seen when we've done the plots that you can get them through the model object. Okay, so if you want the fitted values, you can just do the model object $sign fitted values. Okay, you can also use the predict function. Okay, so if you have ever used LM or GLM in R, this should look very familiar. Okay, so if you want to use predict, you can do predict on your model object, and that also gives you the fitted values. It's the predicted values for the values in your data set. And if we want to think about doing predictions for new data, okay, so here we're kind of interested in forecasting rather than just looking at the fit for the data we already have. So we can, again, still use the predict function. So the first argument is going to be our model object, okay, so GAM6. And then we pass in new data equals our test data set. And this will give you predicted values of confirmed cases for your test data. Okay, so I'm going to call that sort of test predictions. Okay, and if we have a little look at that, okay, so you get your predicted values for each one. So what we can do is we can plot our training, our test data. Okay, so let's look at this. Okay, so plotting our test data. Now, unfortunately, as is often the case with real data rather than sort of nice examples, is that we do have this sort of quite a big change towards the end of our test data. Something sort of new has happened. So we can think about, let's look at, does this, can our model capture this, or how well or how badly does it do? Okay, so let's plot our test predictions. I've done something again. We just look. That should be correct. This should work. What I'm going to do here, I can't see off the top of my head what I've done this time. So here is our predicted data for tests, and we are plotting our fitted predictions. So this is a testing data for OBS. This is going to annoy me until I figure out what it is. Now you get to watch me finding bugs. Yeah. Ah, yes, new data doesn't have an underscore in it. Thank you. Yeah, so predict was returning too many values. Because the argument new data doesn't have an underscore in it. And R is wonderfully didn't give me an error message about that at all. Nope. This. Okay, finally, there you go. So you can see that our forecast isn't working particularly well here. Okay, so it's capturing the sort of some of the seasonal components, but because we have this sort of big change in our smooth fit in terms of forecasting into the future, it's not working particularly well. And there's a couple of reasons why this might not be working super well, and we'll come on to them in a little bit. But it's thinking about, again, if you've overfitted your data and you have this very complex relationship, or is the nature of real data is that the relationships change over time and the unexpected things happen. But for the sort of smooth fit initially, it's not doing too badly in the sort of grand scale of things. What we might also want to do is think about interpreting our models. Okay, so we've seen in the previous section that we can plot the smooth fit for each of our predictors, for each of our explanatory variables. But in terms of what does that mean for forecasts, or what does that actually mean in terms of how much do they contribute to the model? One of the nice features of the predict function for GAMs is that you can get predictions for the smooth values of each of the terms. Okay, so you can do predict type equals terms. Okay, and I'm just gonna look at the first couple of rows of this data. Okay, so what you get here is the predicted smooth values. Okay, so for each row in our test data, we do have actual values of sort of date obs and for day, but it's thinking about what's the smooth values of these and how much do those contribute to the prediction. So if you think, what actually, how do we get these predicted values that the predict function, what's it actually doing? Is essentially adding up the smooth terms plus the intercept at each point in time. Okay, so if you were to look at, let's say, the output from the predicted terms for the first row and add together the sum of these values, okay, so add up each value in each row alongside the intercept, okay, so you can get that with the coef function, okay. This gives you the predicted value. And if you compare that to the first fitted value, okay, you get the same thing. So GAMs aren't as easy to interpret as linear models, okay? But you can say for each sort of point in time, for each individual forecasted value, what's the contribution that's coming from the date, what's the contribution that's coming from the day, and if you have other variables in there, you can sort of say what's the contribution for this particular forecasted value from each of those different terms. So it makes it a little bit easier to interpret than some sort of more complex machine learning models, for example, is that you can still break it down into each of your different explanatory variables and thinking about the contributions that those each are making. Okay. So I can see there's a few questions in the chat. So some of them are around sort of variable selection. So how do you decide which variables do you include in a GAM? And someone has very helpfully linked to the sort of step.gam function. So if you are using stepwise feature selection for LMs or GLMs, there are essentially similar implementations for GAMs as well. Personally, I'm not a big fan of stepwise selection methods. Depending on whether you're going forwards or backwards, you can sometimes end up with wildly different models. For me, when it comes to sort of variable selection, it's thinking a little bit more about the context and thinking about what might be important to include. So I always kind of start with that. And the other thing that I'll come back to in a second is thinking about collinearity between features in your model. So like any sort of regression based model, if you include two variables that are one is maybe a sort of some function of the other, then you can get sort of unstable estimates, and that sort of suggests that you probably don't want to include both of those features in your model. You get the same sort of things with GAMs. So if you were, for example, if you're thinking about the COVID data, okay, you have a column that's people vaccinated and you have a column that's people fully vaccinated. One of those is likely some function of the other. So thinking about does that actually make sense to include both, or do you only need one? I think variable selection is generally a difficult problem, and there's no automatic way potentially. There are things as you kind of mentioned in the chat, things like elastic nets or things like lasso regression, which you can use for automatic variable selection for linear models. But generally, it is one of those questions that has no straightforward answer. The other problem I'll probably mention with GAMs is that if you are including, not necessarily if your data is particularly large, but if you are including a very large number of parameters, they can get computationally very difficult. So it's one of those things where including lots and lots of potential features in your model computationally might not be as much of an option. So it is thinking a little bit more about which are the, in terms of context, what's the most important things to include. And yeah, my answer I think will always be go and think about domain expertise and talk to people who know, in this case, lots about COVID and what confirmed cases might be based on, I think would be my initial step for variable selection. So we'll move on to some more exercises. As always, the code for this example, a variation of that is up on GitHub. But for exercise number 3, what I'd like you to do is run the gam.check function on the generalized additive model that you fitted in the previous exercise and look at, do you need to sort of refit it? Do you want to use a larger number of basis functions? Have a look at the fitted values, make some forecasts for the test data, and then have a look at the contribution of different terms in the model. Okay, so again, I'll give you some time to work through that. Do you just sort of let me know in the chat when you're kind of ready to move on to the next section? Yes, I will send the. So this is a link to GitHub. I'll post that in the chat. So if you go into the exercises folder and go into exercise 3, it'll give you the sort of prompts for the exercise there on the slides. And the solutions are on GitHub as well if you do want to sort of start by running the code. I can see there's another message in the chat, which is absolutely not a silly question. It's I would say quite a complex question. So in the case that you consult some domain expertise about particular variables, and they say it's an important variable, you should include it in the model, but it doesn't actually seem to help statistically. Should you still include it in the model? And I think it depends a little bit on what you want to do and why they think is important. So it might be that you want to see what is the effect of a particular variable given the other variables that are in your model, in which case you could include it and then sort of say, when you also account for X, Y, and Z, it doesn't seem that this is as important. The other thing I'd probably ask is, rather than thinking about the way you frame it when you're talking to domain experts, rather than sort of putting the binary question of, is this an important variable? Because the answer will always inevitably be yes, because everything's important. But you can think more about what's the most important. So asking them to sort of almost rank the particular variables for you as well, and sort of starting with, okay, if I include their top 3 most important versus including the top 5 most important, I think would be one way to sort of approach that, is that potentially every variable is important, but think about the ranking of which ones might be most important in domain expertise. Okay, so another question in the chat. Thinking about why was the rationale behind including date as a smoothing covariate? It is mainly aimed at smoothing out bumpy case counts. Okay, so if you want to make forecasts for the number of confirmed cases over time, when you're thinking about forecasting for a trend, for example, you don't want to be including sort of all the bumpiness of that. So it is mainly about, yeah, smoothing out the cases over time. So what you could obviously just fit a sort of generalized linear model, and you could try to include some function of date over time. But the idea is that when you look at the trend of things over time, so if we go back, okay. So the idea is, when you look at the black line here, this is your cases over time. And basically you can see there's some overall trend here, right? And you essentially want to try and figure out what is that trend, in order to smooth out the bumpy case counts and think about what's the general pattern of how cases are changing over time, which helps with forecasting. Okay, you don't want to overfit to have all of the bumpy values there. Okay, so another couple of questions in the chat. This is great. I told you that you would definitely have more questions than answer by the end of the workshop, so I'm glad that's true. So one question is, do you need to sort of interpret the smooth pattern, and do you need to think about the impact of, for example, date on other variables? So I think you probably would. Again, it depends a little bit on the purpose of why you're fitting models. But I think if you want to look at the smooth fit to date, you're essentially looking at after you've accounted for changes in day of the week or changes in the number of tests, what's the general trend over time? And that is something that you might want to interpret. Okay, you might want to know what's the general trend in a variable over time. And that's where the smoothing of that particular variable can be useful. You might want to think about its impact on other covariates, particularly when it comes to forecasting. Because when we've looked at the sort of forecasting examples here, if let's say we include things like date, day of the week, and number of tests that were done, okay, if we're forecasting this sort of in real life rather than on test data, then we would know what the values of the date and the day of the week are when we're making forecasts. We wouldn't necessarily know what the number of tests is. So it might be that we also have to forecast the number of tests. And that's where you're thinking about, okay, maybe it has an impact. Maybe tests is also dependent on date. So I might have to model tests as a smooth function of date to get a predicted value for tests before I can put that into my forecasted model. I think, yes, you might want to interpret it on its own if you want to understand general trends, but you might also want to think about its impact on other covariates, particularly those that you will also need to forecast in order to make forecasts of, for example, confirmed cases. Another question is, can you if you want to compare, for example, GAMs with let's say GLMs, basically, can you do it with sort of AIC? So the thing with AIC, so I think what I think you might be wondering about is when you try to look at AIC with things like ARIMA models, it doesn't work because the number of data points in the underlying models isn't the same. Okay, so when you do things like AIC, you have this lag. So you don't have the same size of underlying data in different approaches when you're comparing sort of ARIMA to, let's say, regression. It doesn't work because the data sets aren't the same. If you have lagged values in AIC, you lose a couple of data points. So generally, when you're looking at AIC, you need to make sure the underlying size of the data that you're using is the same. Another kind of a comment in the chat. We will move on to the next section in just a second. But yeah, you kind of pointed out when coming back to the having to predict the values of covariates in your model before you make your actual forecast can introduce a large amount of uncertainty. as well, because you have the uncertainty in what the value of the covariate is, and sometimes that's not acceptable because it just increases the amount of uncertainty. So that is another potential thing when you're thinking about variable selection, particularly when you are thinking about forecasting as which variables will I actually know for the time that I'm going to be making a forecast for, and potentially using that as a starting point to avoid adding that extra layer of complexity. One question in the chat that I can answer reasonably quickly. So the question in the chat was around can you get confidence intervals for your predictions? You can get standard errors out of the predict function. Okay, so we have our test predictions $fit. If you do test predictions $, you get standard errors for the fit. Okay, so this gives you the standard error for each, and you can get sort of intervals based on those. Okay, I am aware of time, so I will try to come back to questions again at the end, but I want to kind of end with what happens when GAMs don't actually work very well. So I think we've mentioned a couple of these problems already. So you can get unstable estimates if one of your smooth terms is approximately the same as some combination of other smooth terms. And that's a general problem in not just in GAMs, but in sort of GLMs or linear models. If you have two variables that are highly correlated, you're going to have problems. I've also mentioned they can be computationally expensive for large data sets. And by that, I do mean more large in terms of number of parameters. There is a function BAM, okay, so BAM, still within the MGCV package, which has some a slightly more computationally efficient implementation of GAM, and it essentially works exactly the same way. So if you are sort of coming up against limits on how long things are taking to run, it might be worth having a little look at the BAM function instead. The other two things I want to mention, which do sort of have solutions. One of the assumptions of generalized additive models is that you have independence between observations. And very commonly, when we're working with things like time series data and we're looking to do forecasting, you very rarely have independence between different observations. Okay, so things are generally dependent on time. So if you're thinking about things like autoregressive models or sort of extending to ARIMA models, thinking about what happens today might be quite related to what happened yesterday. So you don't necessarily have that independence. And I will quickly go through an example of the GAMM function. Okay, so that's generalized additive mixed models that show you how you can deal with dependence between observations in a minute. The last thing I do also want to mention, and something you've seen an example of, is that you can get quite unstable predictions outside the range of the training data. Okay, these sort of basis functions and the general smooth fit is based on your training data, and it can be quite a complex function that when you go outside behaves in sort of unexpected ways. So when you're trying to forecast forward, you get these sort of unstable predictions. And there is reasonably recently a sort of paper on dynamic generalized additive models with an associated R package. So it has this MV GAM function, which looks at a kind of Bayesian approach to dealing with predicting and forecasting using GAMs. So if you are specifically interested in GAMs for forecasting, I would recommend you look at that R package, and I think I have a link to the paper at the end as well. Okay, so to come back to the kind of point around thinking about our observations independent, okay, we quite often look at things like ACF plots, so looking at autocorrelation or observations correlated with observations in the past, right? And you can see that if you look at the confirmed cases and you look at that ACF plot, yes, there's definitely some autocorrelation there. They're definitely not independent observations. And so, if you weren't thinking about GAMs, you're probably thinking about some sort of ARIMA model. You might do some sort of regression first and then model the errors with an ARIMA model. And you can do that with GAMs as well. So it's very confusingly also called GAMs, but with two M's. So looking at generalized additive mixed effect models. And just like sort of standard GAMs, you can have nonlinear relationship between predictors and response variables. So you have these smooth functions. But you can also include random effects within a model. And crucially, this includes adding in correlation structures for the errors. So I will go through an example of how do you do this in R. Okay, so start off looking at the ACF of the residuals. Okay, so if you think we've fitted GAM number 6, and we can get the residuals from that model and look, is there still some relationship in there that we're not seeing? Okay, it definitely looks like there's still something in there when you look at the ACF and the PACF. Okay, so you can start to look at these and sort of pick out, is there some relationship in there that we're missing? Okay. One thing I do want to point out is that in this example, our data is not equally spaced, right? And usually when we're thinking about autoregressive models, it assumes that we have regularly spaced data with no missing values. Okay, so the way that we fit generalized additive mixed effects models, okay, is using the GAM function with two M's, okay, and everything in it looks exactly the same as with the GAM function, okay? So if you do a smooth function of date and a smooth function of day of the week, okay? Now, if you just run this and I need data is equal to my training data, okay? All that does is it just fits a standard GAM model. Okay, you haven't added in any random effects, you haven't added in any different correlation structures. So that essentially just does what we had before. If you want to change this, so let's say we have sort of mixed effect model 2, there's an argument in this function called correlation. Okay, and you can specify a particular correlation for that you want to use. Okay, so there's another function, core arma. Okay, so this is going to say an arma model for the correlation structure, for the autocorrelation structure. Okay, and so we can specify what types of models we want. Okay, so let's say we want to fit a model given the date. Okay, so we want to be looking at autocorrelation. And let's say we want an AR1 model. Okay, so usually we express that with P, so an ARP model and an autoregressive model of order P is equal to 1. Okay, so that would fit an AR1 model for the correlation structure with a generalized additive mixed model. Okay, and you can look at because it's a sort of combination of mixed effects and GAMs, it does sort of store it in two different places. So you can look at the summary of the models individually. Okay, so it will sort of give you a general summary of those models. Okay, so you get some nice outputs there, and it lets you include the more sort of time series specific features of autocorrelation when you're thinking about AR and MA models within the context of GAMs, which I think is really useful and kind of a nice feature. And it is also built into the MGCV package as well. So you don't need to go and load additional packages as well. We do technically have some exercises to go through, but I am very aware of time, and I will try to come back to some more questions in the chat because I can see that there are plenty. But I would suggest that you have a look at the exercises if you are planning to use GAMs sort of for time series data. Have a look at the residuals from the GAMs that you fitted and try fitting some general additive mixed effects models instead to see if those are able to capture some of that correlation structure as well. I just wanted to sort of end by pointing you towards additional resources. So I'm sure there's plenty of questions I haven't had the chance to sort of answer. There's very helpfully a list of GAM resources on GitHub, and that has a link to lots of things like blog posts and videos on different use cases on GAMs. I think most of the resources there are specific to R as well. And there is also a sort of GAMs in R course, which is quite nice. It's not specific to time series data, but there's some nice examples there of looking at, for example, binary data. So how do you fit sort of GAMs for binary data as well, which is something that's quite different. There's also a tutorial here on generalized additive mixed models. If you're kind of thinking more about those ARIMA errors and those correlation structures. And this is a link to the paper I mentioned about dynamic generalized additive models for helping with forecasting and sort of stopping those unstable predictions when you're trying to forecast forward into different times. But otherwise, I will leave you with the links again. So there's the link to GitHub, which has it has the data and the examples and the exercises and solutions. There's a link to these slides, and the Posit Cloud project that I've been working in is also public as well. So if you do want to see exactly the code I've written during the session, it is sort of publicly available on Posit Cloud. But otherwise, thank you very much.
Thank you very much, Dr. Nicola, for your interesting session. And thank you very much for accepting our invitation and be our instructor for today's session. So it was an amazing session. So I guess there is no questions on the chat. Also, we'll be sharing all the resources and the recorded video through our social media platform, LinkedIn. So we'll try to share it as soon as possible. Thank you very much. Hope to see you in another Forecasting for Social initiative to get your valuable contribution towards our initiative. Thank you very much.
Perfect. Thank you.
Thank you everyone for joining. Have a great day.
Thank you. Have a good day.